Yeah, let's start the exercises now. Okay, let's hope you can hear me. Yeah. Anyways, okay, I wasn't loud, whatever. Yeah. Okay, yeah. So the first exercise is essentially just a repetition of the proof that the topology generated by the basis elements are equal to the unions, right? So yeah, you just take any A, you take for all x in A, you take the ux, and what? Then you simply take the union of ux, and that's equal to A, and by the third rule, this is the topology. So, yeah. Okay. Yes, let's compare them and determine whether they're comparable, and if so, which is final. Let's go. Okay, so I'm just going to show you the work here. Let's see. Yeah. Okay, I've labeled them from one, can you see it? Yeah, 1 to 3, right? That's going 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So yeah, I'm not going to write the topologies down, all right? They're just going to be listed. Okay. So it's immediately clear that 9 is the finest topology and 1 is the coarsest topology, right? Okay. Now, what topology is just one step finer? That's 4, right? 4 is one step finer, and so is 7, right? So nothing's in between 4 and 7. I should put it even lower, I guess, right? 4, yeah. So they're going finer, right? Can you see 4 and 7? Barely. Okay, should be fine. Yeah. So 1, 4, 7. Then there, yeah. 4 and 7 aren't comparable. That's obvious. What else? Let's see. Now let's start with 7. What's finer than 7? So 2 is finer, right? And there's nothing in between 2 and 7 apparently. So yeah, go one step further. And 8. 8 is also finer. 8 is also finer than 2. So we can go this way, right? Yeah. So is 3, but is 3 finer than 2? It is not. Anything else? Yeah, 9 is finer. We'll get there. 9 is just connecting to everyone from there, so it doesn't matter much. Yeah. 3 is finer than 7, and it's not finer than 2, so it branches off, I guess. And it's not finer than anything else, right? Yeah, it's not finer than anything. Okay, cool. Now from 4, we get 8. Yeah, we do get 8. What else? We get 3, right? We get 6. Is 6 finer than anything else? Yeah, it's finer than 2. So yeah, it's just an exercise. I'm just doing it for some reason, just for thoroughness' sake. Yeah, it's not finer than 2. It is finer than 3 though. Okay. 1, 2, 3. 3 is, I think, complete. It's not finer than 5. Oh, 5. 5 is not. 5 is it unique? Yeah, that's 5. Yeah, there is, yeah, nothing that's finer than 5. It's a direct link from 159. Yeah. And then 9 connects to all of them. So 9 is finer than all. And that's, yeah, how you make it. I am not sure if this graph tells you anything, and it's supposed to be some kind of graph, but it looks cool. Oh, I have attempted it once and I will never do it again. Okay. Yeah, so the finite complement topology is a topology, and now for the countable one. So TC what U x minus U is countable, or x or phi, right? Okay. So x, that's it's there, right? Yeah. So if it's x or phi, then you get x or phi or x. So that's why phi and x are in there. So the first one's done. For the second one, we use De Morgan's laws again. So what we get? We get x minus union u alpha is equal to what? Intersection of x minus u alpha, right? And what is that? That's that's an intersection, arbitrary intersection of countable sets. So that's either finite, countable, or empty. We don't care either way. We get a countable, and that's good enough. Actually, empty sets are countable, so I didn't have to practice. Yeah. What else? For the finite intersection part, we get a finite union of countable sets. And in fact, a countable union of countable sets is countable with the axiom of choice. With for finite, yeah, it's for finite, it's definitely, I think, countable no matter what axiom you use, because at least because the countable finite product is fine. So that's why. Anyways, because of this, this is going to be countable, and therefore, since this entire thing, hang on, is countable, x minus ui intersection is also countable, right? And since this is countable, this thing is in there. So yeah. Now for infinity, it doesn't work that way because so the problem is not that we can't really have an infinite level. So if we could have the minimum, how do I put it? Okay, I'm just stating advanced stuff here, but we could have cardinality omega 1 on its own, right? And omega 1 is basically S omega, and the continuum hypothesis says that S omega is the same as the real numbers. There's a bijective correspondence. Forget it. My point is the problem with infinity is we are not including finite sets here. And a very good example is well, you just take 1, 2, 3, and then all even numbers from now on, and then you take 1, 2, 3, and then all odd numbers from now on, right? What's their intersection? Their intersection will be 1 to 3, right? And that's a finite set. It's none of the above. It's none of the categories, and because of that, it's not a topology. And that's the problem. It's not including all lower levels. If it includes all lower levels, it would still actually be a topology. So if you say it's uncountably infinite, all levels of it or certain levels of it, you have to define that properly. Then I think there would be no, because of the Morgan's laws and some theorem you would have to prove. But yeah, okay. So intersection of topologies being a topology is quite easy to show. Let's see. Yeah. So let's see. X and phi are belonging to all topologies by definition. So the first one is trivial. Now let's say U alpha belong to all topologies by definition. Uh, for all, no wait. Let's see. Yeah, we need an arbitrary union. So beta, and they belong in all U alphas, right? So that's the only way it can actually lie in the intersection. Now we want the union, right? Arbitrary union. So for that to be in all topologies, well, since every U beta is in all topologies, their union is also in all topologies, and therefore in the intersection. So yeah, it's done. And for the finite intersection, same rule essentially. Yeah, it's the same logic. So the quantifiers essentially go in and out. That's the whole deal in this case. Yeah. For the union, I'll give a counterexample, and that should be enough. Let's see. I'll actually just go back to the example one in section 12. So, all right, I think I wrote it down. Yeah, I wrote it down and raised it. I think 2 and 4. So if you union 2 and 4, no, it wasn't 2 and 4, was it? Yeah. Mm, so their intersections must be there, right? Yeah. Mm. There you go, 4 and 5. Take 4 and 5. So we have, I'm drawing it only for this example. What do we have here? Yeah. Yeah. So if we take the union, we're going to get this set essentially, right? Okay. Yeah. This is the union. And the problem with this is that these two's union should also be here. So it's not there. So it's incomplete. But given that we already have at least one of them being a topology, we're always guaranteed a subbasis. And that's going to be the solution for the next one. So yeah, for part B, so yeah, that's why the union isn't a topology. For part B, if we have part C proven, then we can use part B. So I will prove part C, but I'm going to assume part C for the time being. So okay, yeah, it's a subbasis, right? So with part C, there's going to be a unique topology for the subbasis. And that subbasis, which is the union, is going to be the smallest topology that contains all the topologies, since the union contains all. So we just need the smallest topology from that, and from the subbasis we can get that. And the intersection is the unique largest one. So it's the largest one because okay, it's the unique one. For the intersection, I'll try to prove it. It's a topology because well, we've shown it. It's contained in all of them because it's the intersection. Why is it the largest? Mm, isn't the intersection of all topologies, all sets, the largest set that's contained in them by definition? I think so. Hang on. Yeah, you take any larger set, then it won't be the intersection anymore. Any strictly larger set. So that's why it's the largest. So there you go. Yeah. So now let's prove part C, and with part C, we'll also have completely proven part B. Okay. So I've already shown that there's a unique largest topology for each for the basis. Sorry. Oh, I was talking about question 5, not part 3. Sorry. Question 5. Yeah. The basis equals the intersection of all topologies on X that contain A. Yeah. So essentially, if you take an arbitrary topology, we've already shown that if we take an arbitrary topology that contains A, right, then tau prime, which is generated from the basis, A is a basis, is going to be contained in tau. We've shown this, right? So if we take the intersection of, so is that enough? Yeah. Since we've defined, proved that the intersection of topologies is a topology, the intersection of all topologies that contain this will be what? So yeah, you just have to show it's equal to tau prime. So how do you do that? Well, let's see. All of them, all of the topologies are containing tau prime. So we're done this way. And for the other one, well, the intersection is by definition the smallest set that's contained in all the sets. So yeah, yeah. So it has to be the smallest one, and the smallest one is also unique. So yeah, that's how you show it from the basis. So from the containment to the intersection, that was a little bit of work. The main work was in the containment, and we showed that in the proof for the collection C being a basis for that topology. Okay. So yeah, I'm essentially attempting question 5 first. I will attempt part C. It's very easy. So prove the same for a subbasis. That's more important. So it's sufficient to prove that the basis generated from the subbasis is the intersection of all bases that can be all basis collections that can be oh yeah, basis elements and bases, right? There's no such thing as bases. Yeah, my bad. Basis elements. Yeah. So the basis generated from the so basically the finite intersection, right? Yeah, that's the smallest set that contains the subbasis. That's what you have to show. Okay. hmm and then we'll be done because it's just two steps and then there's the smallest and smallest each time. To show the rigor of that, it's a theoretic. Yeah, I'm skipping it. Section one is going to traumatize you if you think too hard about it. But yeah, it's everywhere. And that's why set theory and topology are so connected. Okay, so let this and this contain S, right? What else? Yeah. Anything else you need? Okay, so this is any basis that contains it, and this is the basis that is made from finite intersections. So, okay, yeah, since it's a basis, its singular intersection is going to be contained, and by the principle of induction, all finite intersections are going to be contained. And because of that, this is going to be a subset. So, if this is defined to be the basis generated by the subbasis, then this is containing here. So that's one part of the lemma, and for the intersection thing, you repeat the same argument. You just need to ultimately show this. So yeah, that shows that the subbasis generates a unique topology, the smallest one. So, yeah. Okay, C part. Yeah, find the smallest topology. Oh yeah, even that's a great example, right? Since they aren't intersecting, I think that's how it works. Yeah. So that's also a good example. It shows the other way, how the intersection isn't there. So phi x singleton A, right? Singleton A and B, singleton B and C, and that's it, right? Yeah. So what's missing here is these two sets is intersection. So singleton B is missing. That's how you get the unique smallest one. And their intersection, which would be these three, I believe, is the unique largest one that's contained. So yeah. Essentially, to solve the problem of part B yourself, looking at question 5 is helpful, but the main hint comes from C since you have to try it out. Yeah. Show that the topologies are not comparable, right? So we have to show that in the basis elements, for some basis element, there exists no basis element for the other that's inside it, for some x that contains that x, right? Okay, so let's start with the RL and RK. RL not being contained in RK, whichever I'm sure what I'm proving here. Let's find out. Yeah, so yes, where were we? So to show that the RL topology, and I'm just going to write the topology as this way, not as tau prime. So that's fine. Yeah, to show that the RL topology is not finer than RK. I think that's what we're going to be showing. Let's take the basis element 0, comma 1 with 0 closed, right? Now, yeah. So for the point 0, you take any element, any basis element of RK. So that means any, yeah, basis element. Well, what does that mean? It will, any basis element that includes 0, if it's an open interval, we already checked, there's no hope. But if we take the open interval minus k, that category, we're still hopeless because it's a subset of the opponent. So yeah, it's not comparable. So what does that mean? That means from this we've proven that RL is not finer than RK. Now we have to show that RK is not finer than RL. And that's how we show two things are not comparable. So for RK, yeah, what should we consider? Hmm. Yeah, let's go with that one only. So, right. Okay. Oh, is it capital K here? I'll just check. Yeah, it is. Yeah, for this one, so, okay, first of all, realize that the this might just be singleton zero might just be open. Let me just check that. Let's see. Maybe not. Mm, okay, so you take 0 and 1 by n and take their, yeah, we have to take intersection. So no, yeah, I don't think singleton zero is open. Sorry about that. Mm-hmm. Okay. Yeah, so this is a pretty good case to consider. Let's take the point 0 and we consider any neighborhood around it. Let's see. Any neighborhood around it. Hmm, yeah. Okay, so it cannot be open at a point ahead of 0 or at 0. If it's open at 0, it's a problem because it's not having 0. So it has to be this clopen interval, right? Again, clopen is bad, but go with me. So it cannot be, so if it's an epsilon greater than 0, we have a problem because it's going to contain some 1 by n, and that's a problem. It's not a subset. And if it's going to be 0, it's not going to contain, right? So here, what about here? Well, if it's 0, then you take any 1 by n again, anything at all, it's going to contain some 1 by n, and that's going to be the problem. So yeah. And because of that, Rk is not finer than Rl. Sorry, I don't know which direction is which. You just think about it. Yeah, I first proved Rk is not finer than Rl, and now I just proved Rl is not finer than Rk. So yeah. Okay. Yeah, let's compare all the topologies of question 7. So the standard topology is probably the courses. Okay, T5 might be. Let's see. So I'll just put 1 and 5. Let's compare 1 and 5. So 5 is definitely, okay, 1 is courses than 5 because for any set of this form, you can have an open interval inside it, namely take any negative n and any, there exists a number between a and minus infinity, take anything, and a, because it's in there, and yeah, namely you need to consider it for the x, right? So just pick x. Uh, there has to be a number greater than minus x, otherwise it's bounded and it's a problem. Just take that number and y comma a, and there you go. So clearly tau 5 is coarser than tau 1 is coarser than tau 5. Now tau 5 is not coarser than tau 1 because finer than tau 1 because yeah, you take an interval, you can't really contain it for any x. You can't really have a subset of it for any open ray. It's called a ray. So yeah, you just can't contain any basis element inside it. So that's, yeah. So what does that mean? That means tau 5 is the forces, and 1 is finer. Let's see if we can go any further. Okay. By a similar argument as the lower limit topology, it doesn't really change much. 4 is definitely finer than 1, and by transitivity, it's finer than 5. So it does work that way. It's it's containment, so of course. And the finite complement topology. Let's see. So mm, I think the standard topology is finer than the. Let's see. So you take any open set that has a finite complement, it's going to just something like that. You take any x, there's going to be an open ray between 2 points at worst, because by density of rational numbers or real numbers, and from that you can get an open interval that's completely contained. So what does that mean? That means 1 is finer than 3. Anything else? Let's see. These two are probably not comparable. Let's see. Hmm. Yeah, probably not comparable. Let's see. Yeah, if we have, let's say, yeah, let's say we have anything that's out of the complement, and then we have an x here, then how do we contain it, right? How do we have something that's contained in the finite complement? So it won't work out. Just visualize the picture. And in the other way, I think they're not comparable. Yeah, it just the set will be too big because let's see, because yeah, the ray has an infinite complement. Every ray has an infinite complement, so it can never actually be contained in it, the finite complement. So they're not comparable at all. 3 and 5 are pretty much done unless we find four. No, two to be. Yeah, two is what. Okay, so I don't think actually there might be. Let's see. Oh, yeah, I think the upper limit topology is different here. There is a comparison with RK. So that's probably why the lower limit topology is preferred. I was thinking there was no difference, but there is. So 3 and 5 are this way, and 4 and upper limit is go. I think I made a mistake. So I thought upper limit and RK were not comparable, but they actually are. So in the exam, I've made this mistake. Anyways, so yeah, two. Let's see. So two is definitely finer than one, that's established, right? I'll just make it directional so it's clearer. Yeah. So if we take this set now, minus k, well, for zero, we do have something. We have whatever we want, right? So for open intervals, we're done. We don't have to worry about them. It's for these sets that we have to worry about. Okay. So let's see. You take any number that's not in k, right? So zero was our best bet, and that's gone. So any epsilon greater than zero, let's see, anything at all. Well, let's see. Yeah, I think zero was the only one, because for any other ones, it's actually similar to the finite complement. So any number greater than zero is going to be between two natural, 1 by n, essentially. And for them, we can just take any open interval even. That's fine. So yeah, then zero was the problem, and it's solved. I think that constitutes an approximate proof that what's finer here. Yeah, this one's finer. Yeah, I think. Are we done? Maybe. Hang on, I just want to check. So how do we prove it? I haven't actually proven it in generality. So, okay, A comma B minus K. Now we need the relevant subset, right? So a comma 0 worst case scenario. If it's something else, we don't really care. Yeah, we don't really care. And then we have what? Closed 0 comma b minus k, right? If this is the case, we don't really care. We can just take anything. We just take a comma 0 exactly. Now for this one, so this is closer to a proof. We can work with this. For this one, yeah, if it's 0, yeah. So this a has to be open, right? Otherwise, we'll have a problem. It can't be closed 0. So then we just take anything that's between a and 0, and then we have a upper limit. So we're fine if it's 0. And if it's not 0, then something less than b that's greater than 0. That's you take any number and yeah, essentially take the use the properties of integers. You can find the least and greatest number in certain categories. So you can find the numbers that are around it. And yeah, from that you can get the open interval. And that's going to be a subset of it. So yeah, as the proof, and that shows that this is the finest topology. Yep. And of course, this is irrelevant now since fineness is transitive. So yeah, that's the order. And I made the mistake of calling them non-comparable in my exam. Oh well, quite scarring given the final result. Oh well. Okay. Yeah. Apply lemma 13.2 to show that this collection, which what's that? Okay, yeah, that's fine. Is a basis, right? Is a basis that generates the standard. Right. Now, yeah, first we have to show it's a basis. No, we just yeah. So any open set is hmm, I don't like how the question is phrased with the 13.2, so let me think harder about it. Okay, so first of all, I'd like to extend lemma 13.2 a little bit more. So given that we know that there's a basis element for a subset of every open set every time, I'd like to say that if we have C that is a subset of this basis element, then it's the same. It will satisfy the hypothesis of lemma 13.2, right? So I'm just saying that that's all we have, right? And this is true because of this, right? So instead of open sets, I'm going to be checking basis elements as I'm saying. Yeah. And C is still a part of the collection, which is a subset of the topology by the hypothesis, collection of open sets. So yeah, that's I'm just changing the lemma a little bit. And what do we get now? Well, every rational number here is an open set, right? Since it's an open interval and it is contained in the basis element by density. So if you take any basis element a comma b, well, there's a rational number between a and b, right? Take it c, right? Let's see, yeah, c. Take any random one, and there's always a rational number between c and b as well, since c is a real number. So take that to be d, and there you have it. You have a member of this set collection that's inside the basis. So yeah, I have slightly extended this way. Yeah. Okay. Now, so now that we have this collection satisfying this property indirectly, we have a basis that generates the topology of standard topology of R. Yeah. Okay. Show that the collection is a basis that generates topology different from the lower limit. And that's easy. You just have to show that the topology that's generated by it is not final or something like that. Actually, I'm not final in either direction is fine. So for that, you just take any a comma b such that a is not a rational number, right? Now what? Now you take any open set that's so not open set here. Yeah. Oh, we have to check up that it's a basis first. Mm, let's see. Is it though? Yeah, it actually is. Okay. Yeah. Okay. So basis. That's there's no argument about that. Yeah. By density of rational numbers and intersections, you can check it out yourself. And from that, we'll get a topology. And yeah, to show that it's not finer, we just have to use that theorem. So yeah, it's not rational. Now what? Now for this irrational A, how do we contain it? How do we have a open set that's containing it? You can't. It's just a zero problem. There's no way. So yeah, we're done, I guess.